Hey everybody, welcome back. We're going to continue talking about electron donating and electron withdrawing groups on aromatic rings. So let's revisit electron donating groups, because a little bit of repetition won't hurt you. Now the X group is anything here, really. By the end of this lecture, we're going to develop a list of things that are electron donating and electron withdrawing. But one of the major things about electron donating groups is that they almost always have a pair of electrons. An electron donation looks like this. Okay? Now, the resonance keeps working its way around the ring. Like so. One more. And you're here. Now, the eagle-eyed among you may have noticed that. Let me finish this off here. The eagle-eyed among you may have noticed that this and this have the same structure, just rotated. And you're not wrong. That's exactly how it works. But they do both exist. So the resonance hybrid now, quick reminder of the rules for resonance hybrids. Your sigma-bonded skeleton is unchanged. You show dashed lines everywhere you have pi bond density in any of the resonance forms, and then you apply partial charges to any place that had a full charge. So the resonance hybrid for our molecule here would look like this. And then you have partial negatives there, there, and there. Easy peasy, Ginny Weasley. All right, so this is for electron donating groups. And the electron donating groups include such thing as phenols, ethers, thioethers, amines, but there's a proviso here we're going to talk about in a few minutes. A-N-A-M-I-N-E-S. Amines. Yay, I did it. Or, less so, but still a thing, the ester, where the sp3 hybridized heteroatom is attached to the ring. So I suppose I should just put an R in all of these for ring. Or and sorry, I made a mistake there. The ring is not there. The ring is here. Because all of these have one or more pair of electrons. Now, there's one more compound I need to show you where it is very weakly electron donating, and it looks like this. An alkyl group can be very weakly donating. Now, all that in mind, let's look at electron withdrawing groups. Now, for electron withdrawing groups, these are molecules that have a cation or a partial positive charge attached to the ring. And we'll list a few out here in a couple minutes. So the resonance forms here would actually be different than the anion because it's one of these little pissy quirks about resonance is cations cannot move. Cations are moved. You got to really watch the verb you use in that sentence. So we're here. One more. Blah, la, 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 la. Okay. And then the hybrid would once again look like this. Very similar to the hybrid we had before, but partial positives instead of partial negatives. Is it the exact same pattern? Yes, it is. And that's about to become important in a little bit. This like every other atom pattern that we're talking about. So let's put together real quick like a list of electron withdrawing groups. So let's start our list this way. These are things that are electron withdrawing. Nitro groups, quaternary ammonium salts. Notice there is a positive charge on the oxygen there, on the nitrogen there, and not a pair of electrons to play with. Also, this. Where X is a halogen. There are a lot more. So what we're going to do is we're going to flip the page and we're going to make a master list of all of these. So let's start once again with electron donating. And there are 3 levels. Strong, moderate, and weak. All right, strongly electron donating groups include phenols, aromatic ethers, phenoxide, and amines. Primary, secondary, or tertiary. Moderate electron donating groups look like this. The ester, where the sp3 hybridized oxygen is right next to the aromatic ring. Amides in the same basic form. Now this can either be a primary or a secondary amide. And there you go. Weak activators include, weak electron donating groups include that R group. All right. Now let's move on to electron withdrawing. Groups. Weak. Halobenzenes, where X is Cl, Br, or I. And I know this goes against the fundamental rule that you only have that pairs things with pairs of electrons or electron donating, the halogens have enough electronegativity that they can make it difficult. Moderate electron withdrawing groups. Look like this. All right? So the R can be an H, in which case it's an aldehyde. The R can be a carbon, in which case it is a ketone. The R can be an OH, in which it is a carboxylic acid. The R can be an OR, in which case it is an ester. The O could be an amide, or the R could be a sulfonic acid, or R could be a cyanide. The one thing I do want to show you out of this is this carbon right here. The carbonyl carbon bears a partial positive charge. All right? That's what makes it electron withdrawing. Now, I really don't have a lot of room left, but fortunately, it's a pretty small list of strong electron withdrawer. The nitro group, the quaternary ammonium salt, or a trihalocarbon. Now, I'm going to flip the page. I'm almost out of time, but I'm going to flip the page and talk to you about that nitro group. Because you're thinking, oh, nitro group, that has a nitrogen. Nitrogen's got a lone pair of electrons. Why is he trying to tell us that this is an electron withdrawing group? Well, it's because in the case of the nitro group, that nitrogen has a positive charge. And that's what makes it very strongly electron withdrawing. The same principle holds here. Where you have a positive charge on that nitrogen there as well. Okay, so this is electron donating groups, this is electron withdrawing groups, and what we're going to talk about in our next video, probably tomorrow, or later on tonight if I get bored, is going to be electrophilic aromatic substitutions. I will leave you with this. These sites are important in any resonance hybrid, the every other site. All right, everybody, have a great day, and I will talk to you soon. And believe it or not, folks, it's almost over.